All right, guys, so here's your video lecture on section 2.3. I'm going to share my notes with you. You can find these guided notes on D2L under the guided notes section under content, or also each week you can find the guided notes linked there. So this says notes section 2.3, evaluating limits analytically. So you remember I said we're going to kind of talk about each topic in 3 different ways. That includes graphically, numerically, like you talked about last week, and then analytically, which means more so kind of like algebraically, plugging in numbers, seeing what happens. So the first thing it says, if the function is continuous, then you just plug in the value. Okay, so what that looks like is if I say the limit as x goes to -3 and 4x squared, well, I just plug in the -3. So 4 times -3 squared. On order of operations, we're going to square this first. So we get 4 times 9, which gives us 36. Here's another example. We plug the 1 in for every x, -1 cubed. Oh, whoops, not plus. Minus 1 plus 2. And then we order of operations. We cube this first. And then this negative stays in front because it's technically a coefficient. It's technically -1 times x cubed. So this is -1 minus 1 plus 2. And so we get -2 plus 2, which gives us 0. All right, this one I plug in -2. I get 2 times -2 squared minus 6 times -2 plus 5 over -2 minus 3. So we get 2 times 4 when I square that. A negative and a negative gives me a positive, so plus 12 plus 5 over -5. So I get 8 plus 12 plus 5 over -5. So that's 20 plus 5 over -5. So -5. And if I plug in this one, I plug -2 in for both of those. -2 quantity cubed minus 6 times -2, and then take the square root of that. So I get 8 plus 12. And so that gives me the square root of 20. Or if you want to simplify that, 20 is 4 times 5. So it's like the square root of 4 times the square root of 5, or 2 root 5. So basically in all these situations, you have just a normal looking graph that's continuous. And so at every single C value, the value and the limit equal one another. So you just directly substitute it. So I'm going to clear this and move down to the next section. I'm going to go through quickly these properties. And these are just limit properties. So basically, if you have the limit as x approaches c of k, if k is just a constant. So say I had like the limit as x approaches 3 of the constant value 2. This is the y equals 2 line. So it's like you have a function at y equals 2. And so no matter where you are, for whatever x, wherever x is, y is always at 2, or that k value. So this one would be 2. This would just be k. This is a property that the limit of the sums is the sum of the limit. So we can just split this apart, or difference. You can pull it apart and evaluate each part separately. This, you can pull the scalar multiple out front, k times the limit as x goes to c f of x. This, you can multiply the product of the limits times one another. This will make more sense when we see it in examples. This one is the same. You can divide the limits for one another. And this one is you can find a limit and then raise it to the n power. And so those are just some limit properties. The same for here. You can take the nth root of any number, and I'll go ahead and write it out for y'all. So this is the same as the nth root of the limit as x goes to c of f of x. And this you can say f of the limit as x goes to c of g of x. So you find that limit, plug it into f. So now we're going to apply some of these. Let's see what happens when you apply them. Find the limit given these things. So the limit as x goes to 2 of g of x. So I just find g of x, which is right here. Oops, no, right here. And I plug in 2. So I'm going to plug 2 into each x. Substitute 2 into each x. So this is 4 times 2, 8, minus 2 to the 4th, which is 16. So your answer is negative 8. This one, we're going to substitute negative 8 into the f of x function. The cube root of negative 8 is negative 2. And this one is saying plug 2 in for g, and then plug that into f. So plug 2 into g, which we did over here actually, negative 8. And then plug negative 8 into f, which is actually what we did here. So the answer would be, we know that f of negative 8 is negative 2. We just did that. Given that f of x equals x plus 7, g of x equals x squared, find the limit as x goes to negative 3 of f. So that would be negative 3 plus 7, which is 4. This would be 4 squared, which is 16. And this would be negative 3 plus 7. And then g of 4. So that is g of 4, which is what we did here, which is 16. So that's just practicing some algebra skills, plugging in for the limits, using some of those limit properties. Okay, so all the limits of transcendental functions. I'm not going to write all these out because I think it's helpful to see the examples. This whole entire section, you're just substituting c. Basically, this is just you substitute and you see what happens. Every now and then it will be undefined for certain values, but you're going to plug in c, and then that's the limit as long as the function is defined at that c value. So let's actually see what that looks like when we go to evaluate some of this. So find the limit as x goes to negative pi. So 4 cosine of negative pi. Now, I do have a video saved for trig, kind of a quick recap of trig. This is, when you think of the unit circle, here is 0, this is pi over 2, this is pi. It would also be negative pi if I went this way. And so what is the cosine value here? That's the x value. So the cosine value is this one, which is negative 1. And so it would be 4 times negative 1, which is negative 4. This one, I'm going to plug in pi over 3. So we're evaluating tangent of pi over 3. Pi over 3 is right here on the unit circle. And its x coordinate is 1/2, and its y coordinate is root 3 over 2. And tangent is y over x. So that would be the square root of 3 over 2 times 2 over 1, because we're dividing by 1/2. And so we get the square root of 3. This one, I plug in 7, so secant of 7 pi over 6. This is really just kind of a review of trig. Do you know your unit circle? And again, I have a whole separate video for that. So 7 pi over 6. This would be a 6 pi over 6. It's all the way around. And so this right here is 7 pi over 6. The coordinates here, I went over a lot, down a little bit. So that is negative root 3 over 2, negative 1/2. Both are negative. Now secant is the reciprocal of cosine. Cosine is the x value, so secant is the reciprocal of that x value. So it would be 2 over the square root of 3. Or if you want to rationalize it, it would be 2 root 3 over 3. Again, if the trig unit circle stuff seems a bit fuzzy, go check out that other video. And also I have one for logs and exponents, just kind of a quick review for that. The big thing you need to know is that the log of 1 is 0, and e to the 0 is 1. So here, if I plug 1 in, I have the natural log of 1 over e to the 1. The natural log of 1 is right here, and that is the key point, which is 0. So you have 0 over e. E is just a number. It's like pi. Okay, it's a transcendental number. It's 2.7. So actually, its definition is a limit of a function, but you don't have to worry about that right now. So the answer is 0 over a number. 0 over any number is just okay. Some people get confused. A number over 0 is no, doesn't exist. But 0 over number is okay, it is 0. So there are a few examples on trig. Clearing the screen so I can move down. Okay, now this here, when I taught calculus for my high school students, I spent most of my time talking about this form right here. This indeterminate form. Now, you always should check anytime you have a limit with a constant, because that's what we're talking about here, where x is approaching some constant. You always just plug it in first, and if you get a number, you're done. That's like all of the previous examples we did, including 0 over a number. That's okay. 0 over a number is 0. If you get a number over 0, which we'll talk about in a few sections, this is D and E. So it's either positive or negative infinity. You have to look at the one-sided limits to tell. We'll talk about that later. But most of the time, you're going to get this guy, 0 over 0, which means most likely there is a limit. So this is, oh, more work to do. That more work is this stuff right here. Factor and reduce the expression. Now, I'm going to give you a key with this. If x is approaching c, usually the problem factor is x minus c, which I'm going to demo in this one up here. So you're trying to get rid of x minus c in the top and the bottom. So it will cancel, and you'll be able to plug into whatever else is left over. Rationalized radical, we're going to talk about this. Rationalized radical, the square root of a plus the square root of b, the conjugate of that is the square root of a minus the square root of b, and we'll talk about that. And you multiply by the conjugate so that you can get rid of that radical. Simplify, sometimes that's if you have like a common denominator you need to find. Clear the complex rational expression and then take the limit again. So those are some helpful hints. So first, your first step is to always plug in this number. This time I get 4 plus 1 over 4 minus 4, and I get 5 over 0. Which remember, no, this means D and E. No limit. But this one, when I plug in 4, I get 0 over 0, which means, oh, more work to do. And since I see that I have a quadratic on top, you're going to factor. Now, this is your cheat for those of you that are not strong in factoring. This tells you the factor you're trying to get rid of. X minus this number is what you hope to find in the bottom. Hey, he's already there. And in the top. Well, guess what? X squared minus 16 is a perfect difference of squares, which can be factored as a minus b times a plus b. So x squared minus 16 is x minus 4 times x plus 4. And so I can simplify that, divide out the problem factor. And now this, essentially there's a hole in the graph there. And so this graph actually looks like the line x plus 4 with a hole in it at 4. So now we're going to plug in 4. 4 plus 4 equals 8. And so what this graph is it's like the line x plus 4. And at 4, you have a hole, and the hole is up at 8. And we were able to figure that out by factoring the top and the bottom, simplifying that factor, and then plugging it into what is left over. So that's the key. X approaching c, if you're factoring x minus c, is kind of a helpful hint if you're stuck. So let's try these. This one on the left, 17, is a factoring one. So we're going to plug in -5 first. That's 25. Then that would be -5 minus 20. So then that is 0. And that would be 25 plus, oh no, minus 10. Yeah, so we got 0, 0. Now, I said this gives you a clue. X minus that. What happens when you subtract a negative? You're really adding it. So this is kind of like your key factor. So I'm just going to write that down and hope that it works out. Let's check it out and see. Well, if this top one is x plus 5, the only way I'm going to get x squared is if I have x times x. And the only way to get negative 20 is if I have 5 times negative 4. So let's test it out. If I did x times x squared, this would be minus 4x plus 5x gives me this plus x minus 20. Here, I want to see what I need to get negative 15. That would be minus 3. So these factor out, simplify to be 1. I plug in negative 5 in the top and the bottom. So negative 9 over negative 8, which would be 9 over 8. Remember, this is just one method. You could test yourself by putting this into y1 like we did last lecture in a table and plugging things really close to negative 5, like negative 4.99999. Hopefully you're going to get something close to 9/8 if we did it correctly. Now this one is, when you see a radical, that's what this is, a square root. The trick is to multiply by the conjugate. The conjugate is just helpful because it's gonna make the square root go away. So it's a plus b, a minus b gives you a squared minus b squared. So you look at the square root, whatever it is, you write down the same square root thing, and then you flip the sign in the middle of the two terms. So this is a -1, so I'm going to put a +1. Now I can't just multiply by a random thing on top. That's not allowed. So I'm going to multiply by that same ugly thing on the bottom. So this is really just a very ugly form of the number 1. That's why it's legal. But we do this because now when I go to multiply this top out, you always get the first quantity squared. So I'm going to get this guy squared minus this guy squared. That's what happens. That's the pattern. So I'm going to get the square root of x plus 3 quantity squared, because it's a squared minus b squared, minus this quantity 1 squared. That's the top. If you were to distribute it all out, I'm not going to write this out every time, but I'll show you if you're going to FOIL it. You multiply first, and then you would do plus the square root of x plus 3, and then it would be minus the square root of x plus 3. So these would go away, and then you get -1. And so then here, when you multiply this by itself, you just get x plus 3, which is what we're going to get here. On the bottom, you just write these things side by side. Do not worry about multiplying that bottom out. So on top, I am going to drop the square root because you're squaring the square root. So it's x plus 3 minus 1. And then you're going to simplify. At this step, you simplify. A lot of people get stuck at this step. That means combine like terms. And remember, you're trying to get rid of x minus that. So the factor I'm trying to cancel out is x plus 2. And I notice if I do plus 3 minus 1, hey, what do I see? X plus 2. That's what I wanted. If I'm going too fast, the good thing about video is you can always pause it and watch it again. So this x plus 2, remember, this tells you you're trying to get rid of x plus 2. X plus 2, x plus 2, what's going to happen? You can simplify it. Divides out to be 1. And we're taking the limit as x goes to -2. So now plug in -2. So 1 over the square root of -2 plus 3 plus 1. So 1 over the square root of 1 plus 1. So 1/2. So when you see a square root, you're going to multiply by the same term with opposite sign in the middle, on top and bottom, and simplify. This section has a lot of examples. So I'm trying to get through. Okay, so this, I want you to memorize these limits. This limit as x goes to 0 of sine x over x equals 1. This is a special trig limit. And then 1 minus cosine x over x equals 0. So these are two that you should just have memorized. This one is, like I said, I mentioned earlier in the lecture, actually, that e is a transcendental number. This is what it is equal to. It goes on, it's irrational. It goes on forever, like pi is also irrational. Now, you don't have to prove these limits exist as 1 and 0 and e. You just need to know how to use them. So I'm going to skip the proof for your sake. If anybody wants me to show you that, I am happy to send it to you. But I'm going to talk about how to evaluate it. All right, now we're looking for the only things that we know. The only things that we know are sine, and it matters what x is approaching. Make sure you're always looking at x going to 0, sine x over x is 1, and when x is going to 0, 1 minus cosine x over x is 0. These are the only things we know to look for. So do you see this guy? Kind of looks like this one, except we just have this extra 2 here. So you're looking for a way to manipulate it or rewrite it to see what you need. So I can rewrite this one as 1/2, just scoot this 2 over, times 1 minus cosine x over x. It's the same thing. I just move the 2 over because I would just multiply 2 times x to get that 2x. And I know that this is 1/2 times 0, because remember I can take the limit of this guy. That's that property rule of the product. So I know this goes to 0. So I know 1/2 times 0 is 0. Now this one, we need to write cosine of 2x as one of its properties. And I'm going to pause just for a second. Yeah. Okay, guys, sorry, I had to run to the bathroom. Okay, so let's do this cosine one, which is a little trickier. So we're going to use the substitution here, which is on that trig sheet that you have. I'll post it this one. So we see that on there, cosine squared or sine squared theta equals 1/2 times 1 minus cosine 2 theta. And if we rearrange this to solve for this 2 theta multiplied by 2, so 2 sine squared theta equals 1 minus cosine 2 theta, and then subtract the 1 equals negative cosine 2 theta, and then change all the signs. So 1 minus 2 sine squared theta equals cosine 2 theta. So we're going to make that substitution. So instead of writing this, I'm going to write that. So I have 1 minus parentheses 1 minus 2 sine squared x over x. Then we're going to distribute this negative. So 1 minus 1 plus 2 sine squared x over x. So this goes to 0. And now I want to use my other thing that I know, which is that the sine x over x goes to 0 when we're close to 0. So, but I only have, so this sine squared, I could write it as sine x times x. Times sine x. It's basically like 2 sine x's. And then I have the x. Well, I want to be able to use sine x over x goes to 0. So this is what I want. I see I have one of them right here, and I would like to have another one. So I'm going to make one. How can I do that? Well, if I write an x on the bottom, I also need to write an x on the top. So now this guy also goes to 0. So this goes to 0, this goes to 0, and you're left with 2 times 0 times 0 times an x going to 0. So you have 2 times 3 zeros, so your answer is 0. That one's slightly more complicated. This one's easy, that's just 0. So basically this reciprocal, the same. And then I will show you how to find this, kind of like the work for the longer way. But if you have sine x over x, or actually tan x over x ends up being the same thing, it's just kind of the number, the fraction that you see. So the answer to this one is going to be 3/7. But let me show you why. So I'm going to scoot this 7 over and write it as 1/7. And then we have sine of 3x over x. Now, again, to apply this formula here, this guy and this guy have to match. So if I want this to be able to be 0, I need to make this say 3, just like this says 3. But I can't just put a random 3 on the bottom. I have to also multiply by 3. So really, I didn't do anything. I divided by 3 and multiplied by 3. So now I can say this. Oh, wait, sorry. These both go to 1, not 0. Oh my goodness. I'm sorry I said that. This is 1 times 0. X goes to 0. I am so sorry. Sine x over x goes to 1 times. Sorry, guys. I had a brain fart there. Sine x over x is 1. Sorry, my son just copied me. Okay, so backtrack. Sine x over x is 1. 1 minus cosine x over x goes to 0 when we're approaching x approaching 0. Okay, so in this example, these both should say 1, and then this one is 0. Okay, all that to say, this guy goes to 1, and this is 3/7. So 3/7 times 1 would give us 3/7. But like I said, you can kind of just see that fraction right there. So hopefully that's helpful. And please forgive me for my laps there. All right, now let's see about this guy. So I have e to the x minus 1. Let's plug in and see what we get. First step is plug it in. So e to the 0 minus 1 over the 2 times 0 minus 1. So I get 1 minus 1, which is 0, over 0, which means I need to do something. So we're going to do something kind of unique here. I know if I have something squared, it factors to be a minus b times a plus b, if you have a difference of squares. I'm going to treat this as a difference of squares. If I do that, the square root of e to the 2x, that's like taking e to the 2x to the 1/2 power. That would just be e to the x. So this would factor to be e to the x minus 1 times e to the x plus 1. And then these would simplify. And then you can plug in for 0. So that factor is a little different. I just recognized because they both had this minus 1. And this happens to be this guy squared. So I plug in 0 here. So I have 1 over e to the 0 plus 1. So 1 over 1 plus 1 gives us 1 over 2. Hold on, but not right now. You can later. I'm almost done. Okay. Now this one, we're going to plug in pi over 2 to the top and the bottom and see what happens. Cosine of pi over 2 over cotangent of pi over 2. So cosine of pi over 2 is pi over 2 is up here, and the x value is 0. Cotangent of pi over 2 is also 0 because it's the reciprocal of tangent. So 0 over 0 means, oh, more work to do. So let's see what happens. Cosine, cotangent, you also can reference that here. Trig organizer. Cotangent is cosine over sine. So let's write it as that. Cosine over sine. Now, if you're dividing by a fraction, you can multiply by the reciprocal. So that's like multiplying by sine x over cosine x. These simplify, and now I can just say I'm taking the limit as x goes to pi over 2. So I can plug pi over 2 into sine. And I see up here, it's the y value, so it's 1. So there's kind of a theme, and the theme is, if you get 0 over 0, you have to figure out some way to factor, to use identities, to rewrite it in some way so that you can factor out the problem and see it in a different form. So you can see the answer. It's like the answer is hiding behind that 0 over 0. Okay, this one, I'm going to rewrite like this so you can just see a little better. And this guy, we're going to find a common denominator. That's the trick. I want to remind you just what a denominator is for a second. If I was adding 2/3 plus 1/2, I can't add them unless they have the same denominator. So I multiply this one by 2 over 2 and multiply this one by 3 over 3. And then I could say this is 4 over 6 plus 3 over 6, and I could say, oh, that's 7 over 6. I'm going to do the same thing over here. So x plus 4, I'm going to multiply the top and bottom by this one. And then over here, I'm going to multiply the top and the bottom by x plus 4. And then I'm very carefully going to rewrite this, especially when you have a negative. Be so careful. So I have 4 times 1. So I have 4 minus, I'm just going to put minus parentheses, x plus 4. And then on bottom, you have 4 times x plus 4. And then this is all over x. But that's the same thing as multiplying by 1 over x. You divide by x, it's like you're multiplying by 1 over x. Now, sometimes students do something that's very wrong. And what they do is sometimes they say, oh, I can cancel that out. No, you can't. You cannot do that because that is not order of operations. Also, that's not even what we're trying to get rid of. We're trying to get rid of x minus 0. So x. So what you're going to do first is distribute this, simplify the top, resist the urge to try to cancel out something that actually cannot be canceled in this case. Or minus x minus 4 over 4 times x plus 4 times x. These 4s add to be 0. So now I have negative x over x, which simplifies to be negative 1. And now you can plug in that 0. And if you plug in that 0, plug it in right here, you're going to have negative 1 over 4 times 4. So on top, I'm left with negative 1. On bottom, I have 4 times 0 plus 4, so negative 1 over 16. So here you find a common denominator. All right, this one, I'm going to need some more room. So I'm going to go ahead and clear the screen so I can move the page up. And then we'll be done. This one was kind of a little bit of a longer lecture, packed with lots of information. I have another video on finding limits you can see on my page as well. I recorded a few years ago for some students. Okay, this guy you're going to see later on. It's kind of a precursor to the formal definition of the derivative. But when you see this, you're going to multiply everything out. Expand this out. So this is a FOIL. Now you can, if you just haven't memorized, if you have x plus y squared, it's always this first term squared plus 2 times these multiplied together plus this last term squared. So that's what this is going to be. X squared plus 2 times these multiplied together, x delta x plus delta x squared minus x squared over delta x. Now look over here. I see x squared and I see a minus x squared, which means I can cancel these out. And now I see I have 2x delta x plus delta x squared over delta x. And on top, I see both of these guys have a delta x. So I can factor out that delta x and say delta x, if I divided it out, I'm just left with this 2x plus one of those delta x's. And now I'm going to plug in delta x going to 0. This goes to 0, so I get 2x. And we're going to spend a lot more time talking about that in a few lectures. So the big thing that I want you to kind of remember are those keys. Let's recap. First thing, you always just try plugging in the number. Okay, so that's all these examples, 1 through 4. If you get a number, you're done. The second thing is that a lot of times when you plug in something, you get 0 over 0. If that happens, you have to factor or multiply by the conjugate or find a common denominator or know a special trig limit. So we talked about factoring here. We talked about the factoring being x minus that number. We talked about the conjugate pairs. And then we talked about these special limits here. Sin x over x is 1. Sorry about that faux pas earlier. And a way to remember that is sin x. I remember the I kind of looks like a 1. And for cosine, the O looks like a 0. So sometimes that helps students. So remember sin x over x is 1, then 1 minus cosine x. And that's only when x is approaching 0. It's not always. So be careful that you check that. And then what else? We did those examples there. And then we talked about common denominators and expanding and simplifying. Again, please let me know if you have any questions, attempt the assignment, and let me know if you need help. Thanks.